Hello, good morning. My name is Igor Sasson. As one of the program co-chairs of ISIT, I would like to take this opportunity once again to thank the organizers and to thank actually all of you for your contributions to this conference and for helping us in reviewing these papers and contributing to the success of this conference. It is my pleasure and honor to introduce the next speaker. The plenary speaker of today is Professor Gábor Lugosi. Gábor's research interest includes learning theory, non-parametric statistics, concentration of measure inequalities, random structures, and information theory. Gábor received his PhD from the Hungarian Academy of Sciences in 1991, and during the last 17 years he has been at the Department of Economics in Barcelona. Since 2006 he has been a research professor there. Gábor will talk today on concentration of measure inequalities and the entropy method. It is related in its topic to the Shannon lecture that was given yesterday by Professor Katalin Marton, and we will hear today a talk on concentration of measure inequalities and the entropy method. In this opportunity, I would also like to congratulate you for your book on this topic that has been published this year. So please join me in welcoming Gábor to give his talk.
Thank you, Igor. It's an enormous pleasure for me to be here, and thank you for waking up so early. So I will tell you a little bit about concentration inequalities. So what do I mean by concentration inequalities? These questions can be formulated in many different ways. Some of them you saw yesterday in the Shannon lecture. The way I like to think about this is that we are interested in bounding the random fluctuations of functions of many independent random variables. Okay? So more precisely, we have n independent random variables, and they can take values in any space. They can be vector valued, or they can, it doesn't matter. They take values in some measurable space. And the key assumption here is that they are independent. So throughout the talk, I will assume that these random variables are independent. They don't need to have the same distribution. Okay? And now I have a function of n variables, this f, that is real valued, and I plug these random variables in this function. So this gives me a real valued random variable z, and now I want to know how close this random variable is to its expected value. So inequalities that quantify the difference between the random fluctuations of z around the expected value are called concentration inequalities. In particular, we may be after upper bounds for probabilities of this style. So what's the probability that z exceeds its expected value by more than some amount t? And the same for the left tail. Okay? So this is what I call concentration inequality. Now, there are many ways of attacking concentration inequalities. There have been many approaches, and many of these approaches have developed in parallel. Maybe the first one was based on martingale techniques, starting in the 70s. I just put here a few key names, but of course this is a huge field by now, so don't expect, please, exhaustive references. So martingale methods were the prime tools for a long time, but somehow their reach is limited, and several other methods have been developed that can give more advanced inequalities. One of these methods is that you heard about in Katalin's lecture yesterday is based on information-theoretic and transportation methods. coupling methods. And this goes back to the work of Alswede, Gach, and Kerner in 76, who proved the so-called blowing up lemma, which is a concentration inequality. And then Katalin came up with this new measured transportation method that gave a very elegant and short proof of the blowing up lemma, and then she could go way beyond what could be achieved by martingale techniques. There's no talk on concentration that can avoid talking about Talagrand, who had an enormous body of work in the 90s. He also came up with his own method based on an elementary induction method, which is extremely powerful, completely elementary, but not always easy to grasp what's really going on. So in order to try to understand Talagrand's results, Ledoux established another method which is based on logarithmic Sobolev inequalities, and this is the method that I call the entropy method, and I will try to explain later why the word entropy comes in here. So this is, my talk will be centered on this fourth method, okay? All right. So let's go back to the basics. What do we do when we want to bound deviations of a random variable from its expected value? Well, old Chernoff bounds tell us that it's a good idea to write this probability in an equivalent way. Just take a monotone function. In this case, the exponential function is it will be very useful, and then use Markov's inequality to bound that. Okay? So then in the upper bound, what appears here is the moment generating function of this random variable z. So in order to get good bounds, and this is what Chernoff's technique tells us, in order to get good bounds for deviations of probabilities from these expected values, all we need to do is to get good upper bounds for the moment generating function, and then we can choose this parameter lambda any way we like. We can optimize the upper bounds. Okay? This approach was developed to deal with a very simple, the classical example of a function of independent random variables, which is just a sum. So of course, classical probability theory studied sums of independent random variables very thoroughly, and in the case of sums, the moment generating function factorizes because of independence. Okay, and this is why it was a good idea to put the exponential function here. Okay, so by independence, the moment generating function of a sum is just the product of the moment generating functions of the individual terms, so it just suffices to bounds, to find bounds for these individual terms. Oops. So this is Bernstein. Basically, this method is known as Chernoff bounds, but it was Bernstein who came up with it the first time. Okay, so here's a simple example of a powerful and very simple inequality for sums of independent random variables. So if these independent variables whose sum we take are bounded, then there's a very simple bound for the moment generating function, this sub-Gaussian bound, and if you plug this in Chernoff method, it's very easy to optimize the value of lambda, and you get this very nice non-asymptotic distribution-free inequality, which is called Hoeffding's inequality. Okay. Now, in this talk, I'm interested in not just the concentration of sums of independent random variables, but general functions of independent random variables. So, what can we do if we have sums? If we have general functions rather than sums. Recall, when we have sums, then the moment generating function factorizes nicely, and life is easy. But if we have a general function, well, the martingale approach says that let's try to mimic as if we had a sum here. So how can one do that? Well, this is the so-called Doob martingale representation, named after Joe Doob, whose picture is here, who said that if we have any random variable here, then we can write z minus the expected value of z of the sum of martingale differences, these delta i's, where delta I is just the difference between the expected value of the conditional expectation of z given the first I random variables minus the conditional expectation of z given the first I minus 1 random variables. Okay, so if we do that, then here we have a telescoping sum, right? Because when E sub 0 is just the expected value and E sub n is just the random variable itself. Okay, so we write z minus its expected value as a sum of these differences, and these form a martingale difference sequence. Okay, and now we can use the theory of martingales to deal with fluctuations of general functions of independent random variables. Okay, so here's a very simple example of what one can do with this with this martingale representation. So the variance of z is just the expected value of z minus the expected value of z squared. So that's just the sum of the delta I squared. So if we write it out, this is what we get. And by the martingale property, it's very easy to see that the cross terms cancel out. This is just 0. So the variance is just the sum of the expected values of these martingale difference squares. Okay? So now we can try to see what we can do with these terms here. Okay? Well, so far I haven't used independence at all. Right? This equality is true no matter what. But now if we use independence, then in a few lines one can prove this wonderful inequality proved by Mike Steele, but based on the work of Efron and Stein. That's the following. So take now independent random variables, n of them, and any real valued function of these n independent random variables. Right? So that's this random variable z that we care about. So the variance is upper bounded by the sum, the expected value of the sum of these conditional variances. Now the superscript I means that I only take expected value with respect to the ith variable. Okay, so here I keep all the random variables x1 to xn fixed except for the ith one, and I take the variance, the expectations, with respect to the ith variable only. Okay, so this guy here is a function of x1, xi minus 1, xi plus 1, xn. Okay, and now I take the expected value. Okay, this looks like a very simple inequality, very innocent looking inequality, but it's extremely useful. So I'll try to show you a few examples of why this is useful. The way one can make this inequality useful is to write down equivalent forms of the variance and use it here conditionally. So of course the variance equals the expected value of x minus an independent copy of x squared divided by 2. This is just a simple identity. And also another basic property of the variance is that it's always less than the expected value of x minus any constant a squared. Right? Of course, if the constant here is the expected value, then we have equality. Otherwise, this is always an inequality. Now I can use these bounds for the variance and plug them in here conditionally. Okay? Then here are the inequalities that we get. So if x1 prime, xn prime are independent copies of x1 and xn, so this means that xi prime is independent of xi and it has the same distribution, and all of these variables are independent. And I define zi prime exactly the same way as z, except that I replace the ith variable by this independent copy. Right? So I have this function of many, many independent random variables, and I flip one component, the ith component, I just replace it by another random trie. And now I look at by how much the function changes if I just replace one variable here. Okay? The Efron-Stein inequality tells us that the variance is always bounded by 1/2 times the expected value of the sum of these differences squared. Okay? So notice that if z is a sum, then here what we get is everything cancels out, and what remains is xi minus xi prime squared, and this is actually an equality. Okay? So the Efronstein inequality is actually an equality in the case of sums. So if you want to think about it this way, then you can say that sums are the least concentrated random variables among all in this precise sense. Okay? And it says, intuitively, it has this very interesting and important message, is that if we have any complicated random variable, then which is a function of many independent random variables, then it will be concentrated if it doesn't depend too much on any of its individual random variables. So if we can control by how much the function changes, if we change one variable, then we can say something nice about the variance. Okay? Another formulation of the Efronstein inequality, now this uses the other characterization of the variance that I told you about, says that now I can come up with arbitrary functions f sub I of n minus 1 variables, and I just plug in here in the ith function, I just plug in x1 to xn with the ith variable left out. Okay? And now I look at by how much z and zi differ. And I can do this in any smart way I can to try to minimize the upper bound. Okay? This is another very, very, very useful form of the Efronstein inequality. Okay? So these are pictures of Efron and Stein and Mike Steele, who actually proved the theorem the way I showed you. Okay? So here's a very simple example just to illustrate you how one can deal with very complicated random variables in an extremely simple way. So concentration inequalities are nice because many times you actually don't really need to understand what's going on in order to, you don't need to understand the complicated functions of random variables we have in order to state concentration inequalities. And this is a very nice example of that. So take n independent IID real random variables, and then that are drawn from some density, and then this is the usual kernel density estimate, right? For every data point, we put a little kernel function around it, and we just sum them up. Okay. Now this, if k is a non-negative function integrating to 1, then this is a density itself, and you may want to measure the error of this density estimate by comparing it to the true density and taking the total variation distance, or the L1 error. Now this clearly is a function of these n random variables, and this is very complicated. Right? It depends on lots of things. Depends on k, depends on age, depends on this density phi. So this is, in general, if you want to say things about the expected value of z, you have to understand lots of things. But the variance is really easy to bound. Why? Because all we have to check is what happens if I change one point in my data. So what happens if I replace the ith random variable by another xi prime? Well, it's trivial to see that the L1 error cannot change by more than 2 over n, no matter what you do. Okay? So now we can plug this 2 over n into the Efronstein inequality. Let me go back to it. It's here. So all these individual changes are at most 2 over n. So here we have 4 over n squared, summed n times. So that's 4 over n divided by 2. That's 2n. Okay? So the variance is bounded by 2 over n. And this is non-asymptotic, completely independent of the distribution, of the underlying distribution. So these are the concentration inequalities I like, because you can get, based on general principles, you can get very, very powerful inequalities that otherwise would be very difficult to get. I took this nice example from a paper of De Vroy. In case you wonder, this is not the famous De Vroy. This is her father. And he's actually in town. He joined the protests. Here you can see. Okay. So what else can we do with the Efronstein inequality? There are many cases in which we can control by how much the function changes if we replace one variable by another, but we can actually say something about the sum of these difference squares. So remember, the Efronstein inequality tells us that the variance of f is bounded by the expected value of this quantity here. Now there are many examples, and I will show you a few of them, in which the function that we care about is actually has as the property deterministically that the sum of these differences squared can be bounded by a linear function of the function itself, of the random variable itself. We call these functions self-bounding because this expression here can be bounded by the value of the function itself. Okay? Of course, now the Efronstein inequality tells us that if I have a function satisfying this type of property, then the variance is just the expected value of, is bounded by the expected value on what's on the right-hand side, which is A times the expected value of Z plus B. Okay. A special case is self-bounding functions in which the differences are always bounded. So remember, these f sub i's are functions that I can cook up any way I like, and these must be functions of, so x superscript I in parentheses, that means x1 to xn with the ith variable left out. Okay, so these are the n-1 variables here. So I can cook up these functions f sub i's in any way, such that if I leave out one point, then the value of the function decreases. It cannot decrease by more than 1, and the sum of these decreases is less than the value of the function itself. Okay? So these functions are called self-bounding, and there are many instances of functions that satisfies this, and these are called self-bounding, and these are very nice functions because the variance is bounded by the expected value. So that means that these functions are always concentrated around their expected value. Right? The standard deviation is bounded by the square root of the expected value. Okay? Here I listed a few examples. I'm not going to go into all of them. I will show you one example. Okay? Okay, it looks like my example comes later. Yes, of course it comes later. Okay, so here's so this is the Efronstein inequality. That's for bounding the variance. But of course, in general, we want to know more than the variance. We want exponential inequalities. Now, the first thing that you might want to try is to go back to the martingale representation, the Doob martingale representation. Remember, we wrote z minus the expected value of z as a sum of martingale differences, and now in order to get exponential inequalities, now we don't just want to look at the expected value of the square of this, but we actually want to bound the moment generating function of this sum, okay, of this sum of martingale differences. This is, of course, well known in the theory of martingales, and here I just I'm showing you one example. That's the famous Hövding-Azuma inequality, or Azuma's inequality, in which we suppose that the martingale differences are bounded. Okay, so suppose that when I write z minus the expected value of z as a sum of martingale differences, then all these martingale differences are almost surely bounded by some constant. Right? The ith martingale difference is bounded in absolute value by c sub I. Okay? In that case, even though we don't have independence anymore, but we can recursively peel peel off term by term using the inequality of Hövding that I showed you. Term by term, we can peel off these delta i's from the sum, and we get a sub-Gaussian upper bound. Okay, I'm rushing through this slide because this is well known and standard. You can look it up in many sources. And we get the so-called bounded differences inequality. Okay? Why? Because if I have a function f that has the property that if I change one of the variables by keeping all the others fixed, the value of the function cannot change by more than c sub I, then we call this a function of bounded differences. Then you can easily see that in the martingale representation, the delta i's will be bounded. Okay? So then we can just use the Hovding-Azuma inequality and get this wonderful inequality that's known the bounded differences inequality that says that if I have a function satisfying this, we have already seen an example of such a function, right? The L1 error of the kernel density estimate satisfied this. There the C sub i's were equal to 2 divided by n. Okay? So there are many, many cases like this. Very complicated functions, but if I change one variable, the value of the function cannot change by too much. Then this random variable z that I get by plugging in arbitrary independent random variables in this function differs from its expected value by more than t. The probability of this is less than this nice sub-Gaussian upper bound. And this is exactly what you would get if you had sums of independent bounded random variables. So this is a generalization of Hovding's inequality for a huge class of functions. This is extremely useful and it has countless applications. This inequality was first stated in this form, even though he always, by Colin McDiarmid. He always says that it shouldn't be called McDiarmid's inequality because it had been there before him implicitly, but he made it explicit, so I think this deserves to be called McDiarmid's inequality. It was shown here in an FC Barcelona t-shirt. So the bounded differences inequality is extremely useful. It's very easy to use. It's distribution free, as you saw. It often gives optimal or close to optimal inequality. On the other hand, exactly because of these reasons, because it's distribution free, it's often too rigid, and other methods are called for. So some of you may have come across the contents of this slide by chance, so I think I may just skip it. So what will be very useful for us is this simple and elegant inequality of Tessun Han that says the following. Suppose we have n random variables, and I just assume that these are discrete valued now. One can generalize this easily to arbitrary random variables. So these are discrete random variables. This is the only slides where they don't need to be independent. Okay? So they are not necessarily independent random variables. And x superscript I, that's the same as before. We just leave out the ith variable. Okay? Then Han's inequality tells us that if I look at by how much the entropy decreases if I leave out the ith variable, and I sum up these, then the sum is bounded by the joint entropy of the n variables. Okay? This is very simple and elegant. Here's the proof. It's really elementary. It's just we just write the entropy. This is just the definition of the conditional entropy, right? And the only inequality used here is that conditioning decreases the entropy, right? So if I replaced xi by only x1 to xi minus 1 here, then this entropy increases. And now I sum up both sides of this inequality and use the chain rule, then we get Han's inequality. Okay? So this simple inequality will be tremendously useful for us. So let me show you an example of how the Efronstein inequality can be combined with Han's inequality to get something that I have no idea how by other methods could be proved. So take n independent points on the plane. Okay? So these are now R2 valued random variables. They must be independent, but otherwise they can have arbitrary distribution. They don't even need to have the same distribution. You just throw down endpoints independently. And now I look at the number of subsets of these endpoints that are in convex position. Okay? There are many, many, many of these, right? I just drew 3 examples, right? These 2 points are in convex position. These 3 are in convex position, of course. These are in convex position. Okay? And we count how many there are. That's a random variable that depends in a mysterious way on the distribution of these these random variables. Now, the variance of the logarithm, right, this is a huge number, so we might as well take the logarithm of it. The variance of that log is bounded by the expected value of the log. Okay? This is not asymptotic. This is true for every n and for all possible distributions. So how can one prove such a thing? Well, one can do it in one slide. So by the Efron-Stein inequality, we know that it suffices to prove that this function f, which is the log of the number of subsets in convex positions, is a self-bounding function. Okay? So, and here I use fn minus 1, just the natural way. So this will be the function, the same function, the number of points in convex position based on n minus 1 points. Okay? So if I can prove that this function, the log of the number of subsets in convex position, satisfies these simple inequalities, then I'm done. Because the Efron-Stein inequality tells me that the expected value, that the variance is less than the expected value of this sum squared, right? But the sum squared, because these differences are less than 1, is less than the sum, which is less than this. Okay? So if I can prove these deterministic inequalities, then I'm done. Okay? The first property is obvious. I leave it to you. That's just really a second of thought. So I only need to prove the second inequality. Okay? And this is where this is a deterministic property. So we just fix the points. Okay? So Efron-Stein takes care of all the randomness here. So all we need to prove is this deterministic bound. So let's fix the points. And now this is where Hans inequality comes in the picture. So among all subsets of my point cloud that are in convex position, there are capital N of them, I draw one uniformly at random. Okay? And now let y sub I be the indicator function that the ith point is in my randomly chosen subset. Okay? So this defines a vector of random variables. These are, of course, very dependent random variables, but I know that the joint entropy is the log of the number of subsets in convex position. Why? Because I drew one uniformly at random. Okay? This is just the entropy of the uniform distribution, which is just the function I care about. Now what happens to the entropy if I leave one point out? Well, the entropy will be, of course, less than the log number of points. Right? Because the entropy is maximized for the uniform distribution. That's the only inequality I need here. And then Hans inequality will tell me that the sum of these differences is bounded by, well, because of this little inequality here, is bounded by the sum of the differences of the entropies, which by Hans inequality is less than the entropy, which is just the log number of points in convex position. So this proves that little theorem, which again, I challenge you to prove by any other method. I have no idea how you can do it. Okay. Now, Hans inequality will be important for us not for little examples like this, but in a great framework for proving exponential inequalities for general functions of random variables. So, and because of this, I need an equivalent version of Hans inequalities, which is just rewritten here for relative entropies. So if I have a product measure on a product space, and I have some other arbitrary measure Q, then Hans inequality tells us, and this is really just rewriting the inequality, that the relative entropy of Q and P is greater than 1 over n minus 1. And so these, the Qi and Pi are just the, well, sorry, this should be a subscript here. So these are the marginals of Q and P. Okay, so this is an equivalent way of writing it. And I will explain why we need this form here. And for that, I need to introduce the, well, maybe here I shouldn't use this word entropy in this context, but in function analysis, this is what people call the entropy of a non-negative function. So if I have a non-negative random variable, then I define the entropy as the gap in Jensen's inequality when I take this function phi x log x. So this is the expected value of z log z minus the expected value of z times log the expected value of z. Okay? Because of Jensen's inequality, this is a non-negative function, right? I can define this quantity for any non-negative random variable. And I will call this, with your permission, I will call this the entropy of this random, of the random variable. Okay? Now, if I have now a function of n independent random variables, where this function is a non-negative function, then I can talk about the entropy of this function. That actually it's a relative entropy between the distribution induced by z and the distribution of x. So this word, the word entropy is not that bad. It's a relative. You can think about it as a relative entropy. And if I introduce this notion ent superscript z, right, which is just the entropy calculated with respect to the ith random variable. Okay, so again, I fix all the random variables and I take expected values with respect to the ith random variable only. Then Hans inequality for relative entropies can be rewritten in an equivalent form this way. It's the subadditivity of this entropy. The entropy of a function of n independent random variables, a non-negative function of n independent random variables, is bounded by the expected value of the sum of these conditional entropies. Okay? Now note that there's a nice equivalence between this subadditivity and the Efronstein inequality. If I replace here x log x by x squared, then the entropy just becomes the variance, right? And then this inequality is just the Efronstein inequality. Right? Remember, the Efronstein inequality tells us that the variance of z is bounded by the expected value of the sum of these conditional variances. So you can think about Hans inequality as an entropy equivalent of the Efronstein inequality. It tells us that the entropy of a non-negative random variable is bounded by this expression here. Okay. Now, based on the subadditive of the entropy, now we can prove the so-called logarithmic Sobolev inequalities for certain product spaces. Now, this is not always easy, but there are some cases in which we have very nice and elegant logarithmic Sobolev inequalities. So the simplest example is the binary hypercube. Okay, so suppose now that x1 and xn are independent coin flips, okay, plus minus one valued random variables. So this x is uniformly distributed on the hypercube, and we have a real valued function defined on the hypercube. In that case, the entropy of the squared of z, right? Here I need a non-negative function, so I square z to make sure it's a positive, non-negative valued random variable. The entropy of z squared is bounded by the same expression that we saw on the right-hand side of the Efronstein inequality. Okay? And this can be proved using the subadditivity of the entropy I showed you on the previous slide and a little bit of calculus. Okay? And one can show that in this case over on the hypercube, this is actually, this inequality actually implies the Efronstein inequality. So it's something stronger. And we can hope to get something more out of this inequality. This is a picture of Sobolev. He didn't invite logarithmic Sobolev inequalities. I just like this picture. The logarithmic Sobolev inequality I showed you in the previous slide is due to Gross from 75. So here's how one can use the logarithmic Sobolev inequalities to prove exponential concentration inequalities. And this is a beautiful trick in an unpublished paper of Herbst. So it's now popularly this little argument is known as Herbst's argument. So suppose now I have a function on the hypercube, and I want to prove a concentration inequality for this. So what can we do? Well, we can try to play around with the e to the lambda f, right? Because remember, if I can get good bounds for the moment generating function of f, then I have a concentration inequality. So let f be the moment generating function. And now if I look at the entropy of the squared of this random variable, then if you write it out, then the moment generating function will show up in various forms here. So we will have lambda times the derivative, right? The expected value of z times e to the lambda z. This is just the derivative of the moment generating function minus f lambda log f lambda. So the entropy of g squared, if I choose g to be e to the f half, involves the moment generating function in many ways. Okay? Remember, the logarithmic Sobolev inequality has this entropy of z squared. So now we can check what we get if we plug in this function here in the logarithmic Sobolev inequality. Well, just to keep things simple, let's assume that we have a kind of bounded differences type of assumption on our function. So suppose that if I change one variable by keeping everybody else fixed, that's how we get zi prime, and I sum up these differences changed, then it's bounded by some value v. Note that I don't require that all these differences are bounded. I just require that the sum of their squares is bounded. Okay? All right. So if we have a function satisfying this assumption, and I use the logarithmic Sobolev inequality, then on the right-hand side, I have a very simple expression that also involves the moment generating function. Okay? So now what we get here is a differential inequality for the moment generating function. And this is what this so-called, what we call the entropy method is all about. You start with logarithmic Sobolev inequalities, and these give you differential inequalities for the moment generating function. And if we are lucky, then we can solve them. Well, in this case, we are extremely lucky because we get something very beautiful. If I introduce g lambda as the log of f lambda, then I can rearrange this inequality. It becomes extremely simple. It just says that g lambda divided by lambda, the derivative of this function is bounded by this number v divided by 4, and this is a differential inequality even I can solve. Okay? So we can just integrate it out, and we get a bound for the moment generating function, which is of the sub-Gaussian form, and we get this kind of inequality, which is actually stronger than the bounded differences inequality, because we get something which looks exactly like the bounded differences inequality, but we don't need the individual differences to be bounded. Some of them can be big if all the others are small. Okay? And there are many, many examples in which the bounded differences inequality doesn't give us anything, but this inequality gives us something very strong. Okay? So this is of course only on the hypercube, so we need to do something else. What if we have Gaussian random variables? Well, if we have standard Gaussian random variables, then we can use the logarithmic Sobolev inequality on the hypercube. We can combine it with the central limit theorem to extend it to Gaussian random variables, and there's an exact equivalent of the logarithmic Sobolev inequality for the standard Gaussian measure. And it takes this form. The entropy of any function z squared is bounded by twice the expected value of the gradient squared of this function. Okay? I don't have time to explain too much the proof, but it follows very simply from the logarithmic Sobolev inequality on the hypercube using the central limit theorem. Okay? So if we now repeat the exact same argument, Herbst's argument, to functions of Gaussian random variables, and now suppose that we have a Lipschitz function of a Gaussian random variable, then we get this beautiful Gaussian concentration inequality that goes back to Tzirelson, Ibrahim, and Sudakov, 76, which is as good as you can hope for. Just to try out how good this is, just look at the function f, which equals x1, the first component. Right? That's of course a Lipschitz function, but that's just one single Gaussian random variable, and this is the correct tail behavior of that. And this is true not only for one Gaussian random variable, but any Lipschitz function of n independent Gaussian random variables. Okay. Okay. Now the limitation of this is, of course, now that I had to assume that either I have functions on the hypercube or I have functions of independent Gaussian random variables. But of course, in many cases, we have arbitrary random variables, independent random variables. And this was Michel Ledoux' idea, to try to mimic this argument. Even though we don't have logarithmic Sobolev inequalities for general independent random variables, but we may try to look at what was on the left-hand side when we used Herbst's argument. So this was the entropy of e to the lambda z divided by 2 squared, and try to get upper bounds for this. Using, and as a first step, we always use Hans inequality. We always use the subadditivity of entropy to get the first step, and then you just have to use calculus, and you can get various inequalities, a whole family of inequalities that we can call modified logarithmic Sobolev inequalities. Don't pay too much attention of the exact details here, but the message is that we can using subadditive of the entropy and calculus, we can get similar inequalities to these logarithmic Sobolev inequalities, not as sharp, but they are good enough to get concentration inequalities. So for example, by this method, we can get this general inequality, which now beats the bounded differences inequality, because if we can take any function and look at the differences squared. So here z sub I is just taken to be this function of n minus 1 random variable that I can get by taking the minimum value with respect to the ith variable. So if the sum of these differences squared is bounded by v, then we have a sub-Gaussian, non-asymptotic, dimension-free sub-Gaussian inequality. Okay? So this implies the bounded differences inequality, because if we have bounded differences, that all of these terms are bounded by c sub I, so then this just becomes the sum of the c sub I squares, and that was exactly the bounded differences inequality. Okay? So this implies the bounded differences inequality, and much more. Now here's a very simple, a beautiful application of this. This is an example when the bounded differences inequality doesn't give you anything, but we can get something very strong using the previous inequality. And this is taken from, this example I took from Alon, Krivilevich, and Wu. So they looked at symmetric matrices whose entries are independent. Okay? So all I need is that I have a matrix whose entries are independent bounded random variables, and that's the only assumption I make. They don't even have to have the same distribution. And of course, xij equals xji. So I force this matrix to be symmetric, and then now I want to look at the largest eigenvalue of this matrix. That's of course a very complicated random variable, but I can write it as the supremum of this quadratic form. Now, if V is the corresponding eigenvector, the eigenvector that maximizes this quadratic form, then I can write Z this way. And now it's very simple. I'll skip the details, but it's very simple to see what happens if I replace one entry of this matrix by something else. Okay? So if I replace one entry of this matrix by something else, then you can very easily show that this difference is bounded by 4 times the ith component times the jth component of the eigenvector that achieves the maximum here. And therefore, the sum of the squared changes can be bounded by the sum of this vi vj squares, but since this is a unit vector here, this is bounded by 16, a constant. So what this shows is that the do I have a result for that? No. So what this shows is that for example, by Efron-Stein inequality, it shows that the variance of the largest eigenvalue is always less than 16. No matter what the distribution is, no matter how large this matrix is. Okay? The variance is always bounded by a constant. And we also get a sub-Gaussian, a corresponding sub-Gaussian tail bound. Okay? All right. Now, by playing around with the entropy method, we can get lots of versions of these inequalities. For example, for self-bounding functions that I told you about, we can get exponential sub-Gaussian tailing inequalities. I will just rush through this. For weakly self-bounding functions, we have also a general inequality, which is kind of what you would hope, what you would expect. So we have sub-Gaussian tail bounds where you would expect to have the variance, we have the Efron-Stein upper bound of the variance. Okay, again, you don't need to pay attention to this. Okay, so I want to finish this talk by saying a few words about Talagrand's view of this of the concentration problem. So he emphasized the isoperimetric point of view of this problem, and Katalin also mentioned this yesterday. So here's a very simple setup. So suppose that we have a set in a product space, and we have a random vector that takes values in this space of independent components. Now we can define the Hamming distance of this vector from the set in the natural way. And then you can use the bounded differences inequality to prove this simple inequality. So this random variable here, the distance of this vector to the set, of course satisfies the bounded differences property. So you can get this bound which says that the distance, the probability that the distance is large, if this set is not too small, is going to be tiny. Okay, so this is the blowing up property that Katalin mentioned yesterday. Okay, the proof is really simple, but I don't have time to do it. Now we can repeat this exact same argument by weighted Hamming distances. Okay, so now I can assign weights to each component, alpha sub i's, and I can define the distance, the Hamming distance, as a sum of these, the absolute values of these weights, and then we can get a completely equivalent result for the upper tail of the weighted Hamming distance of a point to A. So we get this upper bound. That for any set, either the set is very small, is exponentially small, or if it is not, then the probability that a random vector is far from the set must be very small. Okay? So either a set is very small or the complement of the blow-up is very small. Okay? So this is the inequality that Katalin also showed us yesterday. And this is true for all possible weightings. Okay? Now, Talagrand showed that, in fact, we can say something much, much stronger. We can put the supremum over all alpha vectors into the distance. So he defined the convex distance of a point to a set by taking all possible weighted Hamming distances, where the weights must be by vectors whose Euclidean normic was 1, and then he proved that this inequality, that either the set is very small or the blow-up in this sense, that the complement of the blow-up of the set must be very small in this sense. This is much, much stronger because now the supremum is inside the probability. Okay? And let me just say that we can prove this inequality by showing in a very simple way that the squared of the convex distance is a self-bounding function, is another example of these self-bounding functions. Okay? And by the way, this inequality can also be recovered from the transportation inequalities that Katalin derived. Okay? Now here's just one little example to finish. Suppose that I have a subset. I have a subset in 0, 1 to the n in the Euclidean space, and now I look at the Euclidean distance to this set. Okay? Then one can show easily that if this is a convex set, then the Euclidean distance is bounded by Talagrand's convex distance. Okay? And this is shown in a few lines by sorry, I'm out of time, so I have to stop here. This can be shown by a simple minimax representation of the of Talagrand's convex distance, and this by this you can prove this this general inequality that says that if I have any convex function of n variables on the hypercube, okay, which is Lipschitz. And now, these random variables can be independent, and all they need to be is bounded. Then the probability that f exceeds its median by more than t has this nice exponential tail. Again, notice that the dimension is not here. So one can get extremely general and extremely strong exponential inequalities by using this approach. So let me finish here, and thank you for your attention.
Thank you very much. Other questions? Yes, please, Sergio.
So here the kind of like the obsession is in getting these exponential tails for the difference, absolute difference. What about, so in a way you could think of this as a non-asymptotic central limit theorem in a way. So what about looking at the relative entropy of this bounded difference with respect to the Gaussian random variable with the same variance? Try to bound that. I mean, that would be another measure of concentration. So there has been nothing.
I don't know. I'm not aware of this.
Are there any questions? Okay. So if not, then let's thank the speaker again.